Thank you. So who are we? This is Ceri, as already mentioned. His real name is Julian Welle. He's a student at Technische Universität Darmstadt. He's active in the crypto group over there, and he's the theorist in this talk. So he'll do all the crypto-like breaking of stuff that we show you later, and I'll talk more about the practical stuff.
This is Alex, or Alec, and well, he does more the practical stuff, and as you can see, he's a professional. He works at this company called Enrons.
Take this one.
Well, they do penetration testing and stuff. Yeah, he's a real funny guy, and if you give him something that is theoretically broken, he starts cranking out practical exploits for it. Yeah.
No, usually. So how did we get here? So what you can see on this slide here is our local hackerspace, the Trollhöhle, which is part of the Chaos Darmstadt ERFA, and that's where we usually meet. And one day we were sitting in the kitchen and we were discussing hash tables for some reason. I don't really remember how we got there, but yeah, happens. You sit in the kitchen, talk about hash tables. And then I remembered that there was something wrong with that, and that Perl, I was a Perl programmer for like 3 years, and I remembered that there was something in the Perl segment page, so we went and looked that up. It's in the section called algorithmic complexity attacks, and that was quite interesting, and that's how we got started, and that's why we looked at all the other languages and saw, did they actually fix something there as well, or, well, maybe they just missed that. So, typically, people do live demos at the end or in the middle of the talk. We'll start with the live demo, and we'll come back to the live demo later as well.
You can still hear me?
Can I just make one? Yeah.
Okay, what you see here is an HTOP running on my computer. Over there you see our network load on my computer for local interface. And well, here I have a Tomcat running. And if I start my exploit code now, and what you will see is that there's a slight increase in network traffic for a few moments, and then you will see lots of CPU load for one thread here. Well, that's everything we're going to show you for now. I guarantee that we will come back to this later, and not much will have changed. Yeah. Yeah, back to our talk. So much for live demonstration. The presenter?
Sorry.
Okay, hash tables. Yeah, it's like that. Has anybody in the audience seen this code or code that looks very, very similar before?
Okay, so for the recording, I guess that'd be about half, maybe a bit less than.
Yeah, this is valid Ruby and Python code, and well, what it does is it creates an associative array called H. It inserts a key-value pair foo as key and bar as value, and then it does a lookup and gets the value bar when it does a lookup for foo. Pretty easy. Who of you knows how this works?
Okay, I'd say probably about 10% or so of the audience knows how this works then. For the rest, we'll explain.
Okay, welcome to Algorithms and Data Structures. So a hash table, basically, at least in the real world, normally it's an array of lists, and if you want to insert a key-value pair, you take your hash function, we will talk about that later, hash your key, so you get an index in your list, in your array, and then you go there, and, well, you insert your key-value pair there. What sometimes happens is that you hash your key and you get an index in your array that has already been taken. Like here, you hash the CMD and you get the same hash value as for login. And in that case, you search this list, and if you don't find it, you append it at the end. It's pretty easy. And well, Those hash tables are pretty neat data structures. Everybody likes them, everybody uses them. They have this cool property that for an average case you have complexity for everything. Nothing takes more than one hash evaluation and one lookup in your array. And if you insert or lookup or delete n elements, you only get linear penalty for that. That's pretty good. Yeah, they're really, really, really fast. Everybody uses them. So this was best in average case, and well, if there's this worst case scenario in which all values hash to the same, all keys hash to the same value. Maybe an attacker has chosen them like that or something like that. In that case, you get a linear complexity for inserting or quadratic for n elements. And well, what happens then is you go to your bucket, you search through this list, and you always have to search to the end because you will never find the key because it's always a different key, but it just hashes to the same value. And yeah, that's pretty bad. Or it tends, we found out this tends to be pretty bad. Yeah, so one thing about complexity is that people always talk, well, this is in XP or NP, or well, this is in n square. What does n square mean? If you have 200,000 colliding strings, you get like 2 MB, is what we just fired on our Tomcat here. And if you have to do quadratic operations for that, that means you have to do 40 billion string comparisons. That takes some time. Even if you do it in one cycle on a 1 gigahertz machine, it still needs like 40 seconds. Okay, this is the second part of our live demonstration. We'll just return over here, and as you can see, as promised, nothing has changed, except for some CPU time. So we are 4 minutes into the talk now, I guess. Yeah.
Slides?
Of course, sorry.
So, as already mentioned, to do so, you need hash functions. I guess probably some people have already heard what a hash function is. So we'll start with a bit of a definition there, and we'll make it by show of hands. So who thinks collision resistance is part of the definition of a hash function? Please raise your hand now. A few people do think so, maybe 20 or so. But yeah, that's not the case. Actually, collision resistance is not part of the definition of a hash function. Who thinks one-wayness is part of the definition of a hash function? No one apparently does so. Who thinks, oh, I spoiled that, fixed output length? Okay, so fixed output length is the only thing that is part of the definition of a hash function. All the other stuff, you might have heard that before, that's when we talk about a cryptographic hash function, but those are not the ones that are used for string hashing. So, who in the room knows this guy? Show of hand, please. A few people, maybe like 10, 15, 20. Well, if you don't know him, that's DJB, Dan Bernstein. That's actually a photo I took last year at last year's Congress of him when he was here and did a talk. If by now you don't know the name as well, look him up. He does pretty cool stuff. He's a researcher, he's a professor, but he also does cool code as well. And the reason he's on the slide is because he also does hash functions. For example, this one. This is DGB X33A. That's one of the hash functions DGB did quite a while ago, and it's a hash function some people actually do use. So what's the name? Where does the name come from? The X is for times, so that's a times 33, and the A stands for add. So what we have here is the only interesting thing that we do have here is the start value, which is 5381, for I don't know what reason. And what else we do have here is the plus asset. So we add, this here is the character. So we iterate over all characters. And we add the character always. This is going to be important because there's another version later which has a bit of a difference there. And that's just a neat way to say this is hash times 33. So it's actually a pretty simple function, but it works quite well for string hashing, and that's why people use it. Or people use similar stuff. For example, Java. That's the Java string hash function. Oh, no, that's not the Java string hash function. This is the Java string hash function. So the red part is the difference. So basically, the only thing that changed here is that here is a 0, and it's not times 33, it's times 31. But basically, same structure there. So let's say we want to find multiple collisions for this hash function. You already know why we want to do that. What do? Well, these kind of functions have a nice property. And the property is that they do have what we call equivalent substrings. So you can write the hash function like this, just as a sum over a product here. And we made a small example there, and you can see, for example, that the hash of EY, or so capital E, lowercase y, and the hash of FZ, for both capital F and capital Z, are the same. I mean, you can find that out either algebraically, because you can see it from the structure here that this must be the case, because this is just 31 less. Or, I mean, if you're lazy, you can also just iterate over all 2-character strings and see which ones have a collision. So, I mean, that's cheap, you can do that. And once you figure that out, you see that in the end, if you append a character, so you say you hash this here, so EYA, what happens in the structure is that basically you have here the hash function of EY, so the 2260 we got here. And you just, well, this is just the last character, that's just the A, the 97. So you can notice that you can replace this here by the hash of FZ. So what you have here is that the hash of EYA is the same as the hash of FZA. And basically, that works for arbitrary strings, so you can just append stuff there, and, well, you get the same hash there. And you can also prepend, of course, so you can do that at the beginning. And that leads to something like this. What you can do then is, well, you can then see that the hash of EZ is the hash of EZ FY, and the hash of FY EZ, and FY FY. Well, and you might notice that this is something like binary counting. So you just count from 0 to 4 here in a binary way, and you just have the corresponding strings that are collisions in the 2-character thing. So well, you can also do that in ternary if you have like 3 collisions for 2 strings. So these collide as well. Then, of course, you can also do ternary counting. And that already gives you like 9 collisions there. So basically, I mean, that was a fixed size, so we restricted ourselves to like 2 characters here, or 2 digits, I'd say. But of course, you can do that for arbitrary number of digits. So for example, if you want to generate 3 to the n collisions, this is just how you can do that. I mean, that's just some Ruby code. But basically, what you do is you generate all strings that look like this, so all 0, 0, 0, 0 to 2, 2, 2, 2, 2, 2 of length n. And then you just replace the characters 0, 1, and 2 by the corresponding collisions. So with that, you can easily generate 3 to the n collisions. And that's one way of breaking those kinds of hash functions.
OK, now I've heard about this neat trick we call equivalent substrings. It works for a certain class of hash functions that have this property. But it does not work for any hash function. And, well, we said before that hash functions have a fixed output length. And what does this mean? Normally, you have this 32-bit integer as output length and internal state and everything else. Do you remember this guy? We're just checking. You do. You also did other hash functions that can be used for string hashing. This is DJB X33X. It's basically the same, but except for one thing. Instead of adding the next byte of the key, the next byte of the key is XORed into the state, and that changes a lot. You cannot do equivalent substrings anymore. And well, this is, I don't know, it's no fun anymore. It's not. We cannot create fast multi-collisions. We can still do brute force. 32-bit brute force takes you a few minutes, and then you have one hit for some value, and then you just do that again and again and again, and you get enough multi-collisions to do your attack again, which we will talk about later how it works. OK. We'll try some different way to break this. So if you do brute force on one target value or one state value, one intermediate state value, you need about, in average, you need 2 to 31 attempts to get there. If you do it with 2, you're twice as fast because it's twice as likely that you hit something. If you do it with 4, again, you're twice as likely to hit something. And if you do it with 2 to the n values, you end up with 2 to the 31 minus n attempts till you have 1 hit. So we will turn this into into a generic attack on the hash functions like that. First thing we do, we assume that we have some way to compute backwards from one target value to an intermediate state. And then we start filling a lookup table with, we could use a hash table here. We start filling this with intermediate state values and suffixes of strings we could hash. So we have a table of, if I get to this value, this is the suffix I use to get to my target value, for example, 0. And then I find preimages to my target value. I just take random strings, hash them to an intermediate value. And if I have a hit in my lookup table, then I append my random string and my prefix from the lookup table, and I get my string that hashes to my target value. And that is really, really, really fast. At least for the case of 32-bit integers. It could look like this. The middle is supposed to be our lookup table. And we have our target value here. This is extremely funny because we always had 2 values there that are the same. But yeah, I hope you get the idea. So this is the hash function again, and we need to compute backwards from one end to an intermediate value. And well, we have to invert 2 operations here. We have a multiplication with 33, and we have an XOR. And we need just a little tiny bit of math to get there. It's not much, I promise. Okay, the first thing is how to invert XOR. It's pretty easy. You do it again. Every element is an inverse to itself. If you do this with multiplication, it's not that easy. What actually is written on the slides is not true. But if you do it with overflow arithmetic and 32-bit integers, it becomes true. It's really, you can, for every odd number, you can get another odd number. You multiply them, you get to 1, at least with 32-bit integers. Yeah, and you can use the extended Euclidean algorithm to compute those numbers very efficiently. If you don't want to, you can use brute force. You just have to do it once. So we end up with this, a function that computes backwards. So does it work? Yes. We take our end, and then we do all the steps backwards. We'll take the last byte first and stuff. It's pretty easy. Yeah. Your turn.
Yes. So that was more of the theoretical part here. Now we're going to talk about how we can actually use that to attack web application platforms. So this is a nice slide showing a bit of the web application world, the landscape at the moment. It's actually from the W3 Tags website, which does some kind of heuristics on the Alexa top 1 million sites and tries to figure out what kind of technologies they're using. And well, there's all kinds of technologies, and PHP, ASP.NET, and say Java are the most prominent ones. And they're colored in red here for some reason, which we'll see later. But just to check who in this room runs or is involved in running a website based on one of the technologies which is colored in red here, please raise your hand. I'd say maybe a little bit less than half as well. So just to check who is involved in running one of those websites with the red technology, would say, well, more than 100,000 hits per day or so. A few people, maybe like 10 or so, 15. So yeah, you might want to talk to your CERT about that, or well, if you are the CERT, then you might want to listen carefully now. So start from the top. Actually just looking at what the general case is. So you have some kind of form, typically on some kind of website. If it's any kind of dynamic website, you have a form where people can input data, and sometimes that's a post request. And the question then is, how does the post data end up in the web application? So as a web application programmer, what are you going to do, and how are you going to access that post data? And I put some different ways to do that for the different platforms in there. The first one is PHP. Second is Java, or Servlets to be exact. And the last one is actually ASP.NET. But one thing to notice is that the structure that you have there for the post data, so like the $_post in PHP, or the request thing in Java, or the request.form thing in ASP.NET, that's always a hash table. So, and well, as an application programmer, you don't need to do anything for that to be a hash table. You get it from the platform. So even if you don't use it, sometimes it is populated by the platform itself, by the language, or the application server. So that's nice from an application programmer point of view, because you don't have to do anything. You don't have to pass the request yourself. It's just already there in a nice hash table for you. But, well, it's a hash table. So as an attacker, you can also put stuff in there, lots of stuff. So starting from the top, PHP. PHP, well, comes in 2 different versions. I guess hopefully most of the people use PHP 5 by now. Well, I'm not hoping people use PHP at all, but, well, if they do, then hopefully they use PHP 5. PHP 5 actually uses the DGB X33A function, which you've seen before, so that is in use there. And it's used on a 32-bit integers. So that can be broken using the equivalent substring attack we already presented. If you're using PHP 4, then, well, that's DGB X33X, and it might be on 32 or 64-bit of output, depending on the platform you're at. So you can break that using the meet-in-the-middle attack that we presented. Well, on 64-bit, that's not really efficient, but on 32-bit, that works very well. Well, then there are some parameters that are interesting for this attack. The first one is the post max size. So that's the size, the maximal size an attacker can send of a post request. So if you have a form, an attacker can put in 8 megabytes of form data in there. And that's typically unchanged unless probably you run some kind of app load stuff, then you might have even increased that. Next thing we have here is the max input time, which is the time as a configuration parameter that limits the time for request parsing, which is actually a good thing that there is some kind of thing like this. You'll see later platforms where there isn't. But it's set to -1 normally, which, well, tends to mean unlimited from the documentation. But as we found out, that's not really true. If you set it to -1, it's actually limited by the max execution time parameter. So that is mostly set to 30 seconds. Or sometimes the distribution changed that. So like if you run a Debian-based distribution, or I think it was a FreeBSD where we tested it, the max input time is actually changed from the PHP default and set to 60 seconds. So that limits the attacker to 60 seconds of CPU time usage for each request. Theoretically, if you really have a max input time of -1 and then a max execution time of -1 as well, if you send a PHP application 8 megabytes of post data, so basically any PHP application, because even though you don't use the post stuff, even though you even don't want to accept post, every PHP page accepts post. So if you have a hello world PHP page, that's going to be vulnerable. And if you send it 8 megabytes of post data, it's going to take like 6 hours and something of CPU time. That's the theoretical case because, well, typically people don't put in their max input time and their max execution time to unlimited. That would be pretty stupid. Realistically, well, you can then just send like 500K data of post, and that gives you a minute of CPU time on a modern CPU, or you send it 300K, and then you get 30 seconds, depending on how your configuration is. You can actually figure that out, how the configuration is, because the server then throws, I think, a 500 internal server error if you go over this limit. So what does that mean in terms of efficiency? So for the different platforms, we always tell you what the efficiency thing is and the effectiveness things. So we've got this nice stamp on the left side, which well, is an advertisement for ISDN. Some people might still remember the times where we had ISDN. ISDN was like 64 kbits. If you had 2 lines, that was 128 kbits. So if you have one ISDN line, or if you have actually like a bundled ISDN line, well, then you can keep one i7 core, like the laptop I've standing there, pretty modern laptop. You can keep that busy all the time if you have one ISDN line. So on the other hand, that means if you have like a gigabit, which, well, there are sockets here somewhere, maybe even on stage, well, then, of course, you can keep a lot of more CPUs busy. Well, that would be 10,000, so that's the little picture there, actually 10,000 dots. They don't need to be on like one machine, because I think you can't really find that machine that has 10,000 cores. But of course, you can kind of distribute that over more machines if you like. yeah, so that's for the, well, effectiveness then. So what's the state on PHP? Actually, I mean, we're responsible guys. We disclose that stuff. It's not like it's a total zero day here. We disclosed that to OCERT, which is the open source cert, and they notified PHP on November 1st. Then we didn't get an answer from anybody, which is kind of bad. And we asked for an update like 3 weeks after that. And that's what the guy said. Well, we are looking into it, and while changing the hash function isn't a trivial change, and it will take us some time. OK, I mean, yeah, more communication would have been nice, but that's the way it is. So actually, then on December 15th, so like maybe 1.5 weeks ago, 2 by now, I think, this appeared in the Subversion repository of PHP. So they actually put in the log, well, they added a max input vars directive to prevent attacks based on hash collisions, which is kind of a workaround. So they didn't change the hash functions, but they are limiting the number of parameters, which, well, works for some stuff. It doesn't work for other stuff. We'll show you later a bit. But we weren't very happy that they, well, for one, they didn't tell us or OCERT that they were doing this, which is not very nice. And then, well, they were putting that into their public SVN. So, I mean, if you read that on December 15th, you might have figured out what the thing here is and that there is a real problem. So, well, yeah, not really that happy. That's in their SVN asset, and that's in their latest 5.4.0, I think it's RC4 release, so it's a release candidate for the upcoming 5.4.0. And I think they're going to change that for 5.3 as well, but we don't have any release date for them because, well, they're not really good at communicating with us. So that's the state there. So what else is there? So we mentioned the next big contender on this market for some reason is ASP.NET, which is like a Microsoft product. That took us some more time to actually figure out what is going on there. So what you get as an application programmer is the request.form thing, which is a name-value collection object. And for some reason, that doesn't use the normal hash table hash function that is used in .NET, which is kind of interesting, breakable as well, but not using the techniques we have shown before. But it uses the case-insensitive hashcode provider.getHashcode method. I really like those long names. And funnily enough, well, this is the stuff on the right, which we just put there. It's a screenshot from IDA, so we put that there to convince you that we are, well, the really good reverses. Well, actually, we are not, but yeah, still, I can recognize that this is DGB X33X. So what you can see here is, well, this is the start value, the 5381 that we saw before. Well, this is the multiplication by 33. And below that, that's actually the XOR of the current character. So, well, we could figure that out, and that works on the uppercase thing. So because that, for some reason, as mentioned by the name, is case insensitive. So first you do the uppercase variant of the string, and then you put it into DGB X33X. If you have like a development server, which you can get for free from Microsoft, and you can try that out, then you can send it 4 megabytes of post data, which seems to be the limit there. And then you get, well, just short of 11 hours of CPU time. So we did that actually again in the Trollhöhle, and we were sitting there, and the CPU spiked, and we saw the 100% CPU, and it was nice. And I was like, how long is this going to last? And then like an hour later, it was still running, and we were like, that is nice. So, but luckily, there's also a CPU time limit. I think I need the... Luckily, there's also a CPU time limit. So IIS, if you run this on IIS, which I think is the typical configuration, because it's a Windows technology anyways, then IIS limits you to 90 seconds of CPU time. So what does that mean in terms of efficiency? Well, there are those things on the left. That was even before ISDN. That's what we called modems back in the days. Maybe some people still remember, maybe some don't, I guess, in the audience. Yeah, so there were like this 33.6 kbit modems or so. So if you have one of them, well, you can keep one of those core 2 cores busy. And on the other end, well, if you're at the Congress and you have gigabit, then basically you can keep like 30,000 core 2 cores busy. So I was trying to make a different picture on the right side with the little dots. But then, yeah, that gets really crowded. So just imagine like the one dot here is 3 CPU cores. And that's going to change later as well for the different platforms. So, well, disclosure state, Microsoft sort of drew the short straw there because, well, that was at the very end of our preparation for this talk when we actually discovered that, because we had to figure out what the hash function was. We were just on the wrong track trying it out with the hash function which is used in .NET, and that didn't work, and then we figured out that it's actually different. So we only disclosed that on November 29th, and we involved CERT with that, and they did a good job to do that and disclose it to them. That's the MSRC case number if you want to talk to Microsoft about it. And they actually talked to us quite a bit, so that was way better than like PHP, for example. So we actually had like a phone conference last Thursday and talked about them, what we are going to say in the talk as well, and had another conference yesterday. So they're working on that and they're taking that very seriously. So the first thing they're going to be working with is like a workaround patch, pretty similar to the stuff PHP does, so limiting the number of parameters. And then they'll be looking into randomizing the hash function, which is the real way to fix that, but Terry's going to talk about that later as well. And there's going to be an advisory very soon, or actually my boss just told me that it should be up already. So if you can try that, there should be an advisory from MSRC about that, where well, they tell you about what you can do in terms of avoiding being hit very hard, but yeah, there's not that much that you can do. You can of course reduce the CPU time, for example, but basically that's the most important thing you can do there. So what else? Yeah, Java. Or you've already seen the string.hashcode function. That is very similar to the DJB X33A. So it can be broken using the equivalent substring. That was actually the example I showed you earlier. And alternatively, of course, you can also do a meet-in-the-middle attack there. So you can get some more collisions, because of course, if you do the equivalent substring stuff, that already has quite a lot of structure of the string. So if you do it more randomly, you get more strings for the same size. And one special thing that is quite interesting for Java is that they actually cache the result of the hash. So like if you have a string object, there's a hash attribute, and if you hash it, well, that gets changed from 0 to the hash value. And well, but that only happens if the hash is unequal from 0. So if the hash ends up being 0, so if we as an attacker choose the target 0, then you have to rehash all the time. That's actually a thing that, well, other people also do as well. So they cache that stuff, but then they change their hash function never to be 0. Well, Java doesn't do that for some reason. Tough luck. So in Java, it's a bit different from like the application developer world. So you have all kinds of different platforms there. It's not like you have the one language and you use that, and that is going to do the request parsing for you. But it's actually done in the Java web application servers. So there are well, all kinds of different web application servers, some open source, some are not. We looked at some of the open source servers. So well, Tomcat, Geronimo, Jetty, Glassfish. And all of them either use the hash table type in Java or the hash map type to store that post data. And they typically have a limit of 2 MB. Jetty being the exception here, which has like 200K, which is way better. So if you have like a Tomcat running and you throw 2 megabytes of post data at it, then well, that's 44 minutes of your CPU time gone. And that's going to mean if you have a Tomcat, there's another of those modem things, so that's an internal one, and so you had like a 9.6K modem as well before the time where we had 33.6K modems. And if you have like 6K bits, then you can keep one i7 core busy. Or of course, well, you might as well keep a lot more CPU cores busy if you have a gigabit. Yeah. So much for Java. The disclosure state, well, we disclosed that via OCERT as well, same November 1st. Tomcat actually has a workaround in their Subversion repository, so they actually published releases for that as well. So that's in the latest releases for 7.0.23, I think, and 6.0.35 and 5.5.35. But I'm not sure if the last one is released already. But they actually worked on that, and they have the same workaround, like limiting the number of parameters. As for Glassfish, Oracle took our advice and said, OK, they're going to fix that in a future CPU, so a critical patch update, and that's just like the ticket number. That's good from the Oracle side. What's not so good is that they said, well, as for Java itself, it doesn't seem like there's anything that would require a change in Java hash map implementation. We politely disagree. Yeah, what else is there? Python. Python actually has a hash function that is very similar to DJB X33X, but it works on register size, so it's different if you have a 32-bit Python implementation or a 64-bit implementation. And well, again, because it's DJB X33X, basically, it can be broken using a meet-in-the-middle attack. But you only get reasonable sized attack strings for 32-bit platforms. And of course, well, in Python, there are different platforms for doing web stuff as well. Plone is, I guess, the most popular of those, and Plone has a maximum post size of 1 megabyte. So you get like 7 minutes of CPU usage for like 1 megabyte request. So, well, you need like 20 kbits to keep one core duo core busy. So we tested on different machines. That's why there are always different cores. But yeah, it's only a matter of a factor as well. So yeah, again, you could keep like 50,000 cores busy if you have gigabit. Well, if it's a 32-bit machine, so hopefully lots of people are on 64. There it's going to be a lot less efficient using this attack. So, same disclosure state. It's a bit, well, unless, it's a bit sorry, the disclosure state for most of the stuff. Yeah, so we disclosed it via OCERT, and then 3 weeks later we're like, well, did you get our message? And they were like, well, this message got held in our moderation queue. Sorry for that. And well, we have Thanksgiving at the moment, so it might take a few days until we get back to you. And we're like, yeah, sure, I mean, that's reasonable. I mean, Thanksgiving is a big holiday in the US, so I guess it's fine. And luckily, they never got back to either us or OCERT, so yeah, that's that for Python. That's well, yeah. And we disclosed that to the Plone guys as well, and they got back to us as third, I think, and well, yeah, but no fixes there, unluckily. Ruby. In Ruby, actually, if you're using CRuby 1.9, you're fine. That's a good thing, because they already fixed that back in 2008. Back when Perl actually fixed that was back in 2003, I think. And for the same reason, they realized then, well, we should maybe fix that. But for some reason, they only fixed it in CRuby 1.9. If you're using CRuby 1.8, which apparently quite a lot of people still do. I was very surprised to hear like the figures from the Ruby people. It's about, on the major platforms there, it's about half or so. Then there's a hash function which is very similar to DJB X33A. Well, you could actually break that for the equivalent substring attack, but they have a different multiplication constant, which makes the small equivalent substrings not so small. So you don't have, I think you don't have any like 2 character colliding strings. So you have to increase those, and that makes it much less efficient. But of course, you can break that using the meet-in-the-middle attack again, and then you get more efficient stuff. So in JRuby and Rubinius, JRuby actually uses the CRuby 1.8 functions as well, both for the 1.8 implementation and the 1.9 implementation. And Rubinius uses something completely different, which is just another Ruby implementation. And typically they have, well, the different platforms on Ruby, like if you're using Ruby on Rail or let's say Passenger or something like this, then the maximum post size is 2 megabytes. So that gives you about 6 hours of CPU time. So who of you guys still remembers the thing on the left? Show of hands, please. Quite a few. So that's what was acoustic coupler. That thing on the left actually gave us like 1,200 bouts back in the day. Well, no, not really. I never had one, but I started with a modem, but similar speed there as well. So if you have like 720 bits per second, you can keep one i7 core busy. So if you have one of those things and you can hook it up to your computer somehow, it's probably going to be hard, but then you can keep that one i7 core busy. Well, or of course, if you have gigabit, then that's going to be a lot, and yeah, you can keep like 1 million CPU cores busy. Yeah, which is going to be fun. So if I wanted to actually change that picture, well, the resolution is the limiting factor there as well, so there would be no space between the dots. So that, yeah, again, then that's 100 CPU cores per dot. Ruby, we're much happier with their disclosure state there, so we disclosed that again on November 1st, and the Ruby security team was very, very helpful, so that was really a good thing that we had going there. So they were very helpful, and we discussed what they're going to change, and they actually randomized their hash function, which is the only real way to change that. So there are new versions, or there's supposed to be new versions. JRuby released something, I think, last night. CRuby should be following any minute now. So they have the patch ready. And well, yesterday was the end of the embargo date, so they should be releasing very soon. And as I said, they randomized the hash function, which is the way to change that. And there's also a new version of the Rect middleware, which is the thing that passes the post request for most of the platforms. And there they limit the number of parameters as well, which is nice. So it's like a defense in depth kind of thing. If you update your Rect and update your Ruby, you're going to be fine. So what else? In the less than 0.1% column on the first slide in the section, there was like V8 or JavaScript in general. So V8 is the JavaScript implementation that is used by Node.js. It's done by Google. It has a bit of a different hash function there. Looks quite different than most of the other stuff. But again, it's vulnerable to a meet-in-the-middle attack. And then again, on Node.js, there's the query string module, which you can use to parse a post request. And then there are lots of platforms on top of Node.js, so we didn't look in that direction because, Node.js doesn't actually limit the size, so there are no efficiency slides there as well. As for the disclosure, we already disclosed that on October 18th, quite a while back. Via OSERT again, got an automated reply back from the Google security team, and then, well, nothing for a while. So I privately contacted one of the Google security team guys I know, and he forwarded the ticket to the Chrome and V8 developers, but apparently they somewhat have a client-side view on the V8 world, so of course it's a lot boring if you have a client-side DOS on JavaScript in your browser. Well, yeah, that's boring, but of course, people use that for other stuff as well. Not that many, but apparently it's a hot thing. People talk about Node.js a lot, so that's why we also included it here. So much for the different platforms. Well, if you're a web application security guy, you might have noticed this is actually just a post request, so there's nothing fancy that you need to do. You don't need to create fancy TCP packets with weird options or so. It's just a simple post request. And that can actually be generated on the fly if you just have HTML and JavaScript. So you could run this attack on a website. So why is that bad? Well, if you have the next big cross-site scripting attack on a big social network or so, then, well, you get lots of participants in your distributed denial of service attack. And that attack, of course, is going to be very, very, very effective. So that's going to be bad as well. And of course, if you just click on a link, then you might involuntarily send those requests to someone you don't know. So yeah, that's the thing here. Yeah, so that was the web application world, which was fun because everybody uses web applications, everybody uses the web. But hash tables are everywhere else as well. So actually, if you parse code, people tend to put stuff into a hash table. So if you like the Java compiler, well, then you parse code and you put stuff you read from the source into a hash table. And then it might take you a while to compile that code. So say if you have a continuous integration system and you just quit your job, and at the last day you commit this huge Java source file into the CVS or SVN or Git or whatever, and it's going to be run overnight, then, well, that might take some time to compile that. That's actually pretty nice because in the web application world, there are always limits, you can only have 2 megabytes. But, well, if it's a source file, it might have been 20 megabytes. What's going to happen then? And then, well, there are also hash tables in your shell, at least on some shells. If you use Bash, for example, there's the syntax to do hashes. And of course, well, as you might have guessed, that hash function is broken as well. So if you actually use that for something, we haven't really found any serious kind of use for that, then, well, you have a problem as well. Well, the live demo, I think we're going to skip that for now and hope you believe us from the slides that this is still running. Maybe we can get back after the Q&A and see if it's still running also.
Well, we also don't just want to tell you how to break things. This is a real problem and, well, how to fix this. Turns out no attacker can compute collisions for a function he doesn't know. At least I've heard so. And also, it's pretty hard to keep your hash function secret. even if you're a closed source product like ASP.NET, people will figure out. So yeah, you should pick a hash function at random every time you start your interpreter, your runtime, or whatever. Or even if every time you start a hash table, you can pick your hash function at random and use that. And well, Perl and CRuby 1.9 already did that in the past, so it's not impossible to do this. And yeah, you really should do this. This is the Perl patch that actually enabled the randomization part in Perl. They had everything ready before. They just used a different hash seed after that point. Yeah, and what can you do if you cannot change the hash function? We already said you can limit the size of the post request in your configuration file. You can almost always do that. You can limit the numbers of post parameters if the target is a web application server, and if it's possible to limit that. And you can impose CPU limits. You can also almost always do that, and yeah, you can fix this problem like that. Well, we only picked on web servers and web applications, and there's different stuff out there, like the Linux kernel. If you look in the Linux kernel for the word hash table, you get 282 hits, and well, we haven't looked into it what it really means, but maybe there's something funny there. Well, back to web servers. There's not just these post requests where you use this and sign to separate arguments. You can also there's also AJAX, and they have some serialization format like JSON for client-side arguments. So if you put your collisions in there, some fixes simply will stop working, and you might get an attack again. You can always think as an attacker like, what will we put into an hash table? If I can control this, I have an attack. Other stuff that you can look at. Erlang, we looked at it. There is a constant hash function, but that's it. Objective-C, there isn't a constant hash function. They change it rather frequently, but always to another constant hash function. There's Lua. We just looked it up, I think yesterday or the day before yesterday. They also use a constant hash function, and maybe you want to break World of Warcraft or something like that. There's GNU ELF binaries, if you want to break your loader or denial of service your operating system, I don't know. And there's Facebook. And Facebook also uses a constant hash function. It's not as easy to find multi-collisions there as it is in other places, but it's possible, I guess. And if there is somebody of the Facebook security team, we would really, really like to talk to them. We haven't reached them yet. Take-home messages. What should you take home from this talk? If you are a language developer, you really, really, really should fix this ASAP. It's not that hard. Maybe some of your users will complain that test cases break and stuff, but really randomize your hash function. It's the only real way to fix this. If you're an application developer, you use your language and you really hope your language developer fixes this, but if they don't, well, think about what stuff ends up in a hash table that an attacker can actually choose. As you have seen, for example, post parameters application developers tend to put them into a hash table. And, well, use something that is not a hash table. There are ways like in Java tree map to do an associative array that doesn't have this problem. If you're a penetration tester, you can also think about what input is controlled by an attacker and possibly ends up in a hash table. And it's really easy to identify what hash function is used. If you hash the empty string and you get the initialization vector of one of the DJB hash functions, then you are almost sure that you have a DJB hash function. Then you hash some short strings, and then you know. And well, at least if you hash the empty string, you almost ever get the initialization vector of this thing, and it really helps. If you're anonymous, we've heard that Anonymous is capable of getting lots of participants for distributed denial of service attacks without XSS. So maybe they want to do something. We don't want to encourage them. Yeah, our thank you slide. Andrea Barisiani from OCERT, he really wrote tons of emails with us. Really great guy. He also was rather fast on picking up on that and understanding this really is an issue, and he worked really great. CERT, after we got them involved, also did a great job of informing the not-so-open source vendors. Well, Perl actually gave us more or less the idea for this, and they already fixed this in 2003, so yeah, hooray for them. Good job. Also, thank you to the people that actually found this in 2003 and made Perl change their hash function. And to the Ruby security team, because they were the only people that really took us seriously. They worked with us. They sent us patches and said, well, is this okay? And we gave them some feedback and well, lots of back and forth. And we ended up with a good solution for this problem. And they are the only ones actually having a fix out yet that will work in future. Yeah, thank you for your attention.
So yeah, thank you very much for this interesting talk. As usual, we have now a Q&A session. And there are 2 mics in each aisle. And people with questions, please line up behind these mics. And then you can ask questions. And maybe I ask a question myself to start. Have you seen any real-world applications of this? Do you know any attack that really has been conducted with this technology? Do you know of any attack that has used this bug or this attack method?
Not except for what we tried, but I guess the people in 2003, they also tried stuff out. So, but I don't know of any particular I don't know of anything that got publicity that uses that.
So I see there's someone with a question, please.
Hello? Yeah, more a comment like a question. You said this is known since 2003, and only two programming languages fixed it. So maybe there's something wrong in how we handle security issues. If there's something known since 2003, and people seem not to notice that it's also an issue in other programming languages.
Yeah, maybe there is then. True, on the one hand, there was like this academic paper, so it's a Usenix security paper from the guys in 2003. And while they were looking at Perl directly, so Perl directly was influenced to change that. But there seems to be not that much interest in looking at that stuff from the other languages. So maybe it makes sense to look at the security patches from the other languages as well, if you're a language developer, and see if that would actually influence your language and whether you want to change something in your language. So we're actually surprised as well that, I mean, this was known and this was very well documented as well in the Perlman page. So people could have known, but apparently, yeah, either they didn't know or they didn't care.
Okay, there's another question on this side.
For ASP.NET, since it's case insensitive, do you need the meet in the middle, or can you just take a long string and change the case?
No, well, that was the first thing we actually tried as well. So yeah, good idea there. But in the end, they end up like the same entry in the hash table as well. So no, you can't just change like the case of the string. That would have been nice, but that's not the case. You actually need the meet in the middle attack there.
Okay, dann haben wir noch two questions from IRC.
Right. Yeah, the internets wonder whether there's an unofficial patch for PHP which they could apply to their web service.
None that we prepared. I mean, there is the patch in the SVN, which, well, is not a real solution, but a workaround, because it only limits the number of parameters. Again, if you're then, say, parsing JSON or whatever, that's not going to be limited, because that's not like the same kind of structure there. But you could work on the 5.4.0 RC4 patch for at least turning off like the trivial exploit, yeah.
Right. And the other thing they wondered is where they can get your T-shirt.
At last year, well, at this year's camp. I don't know if there are any left.
Okay, there's another question up here.
Yeah, I wondered how much does the limit of PHP, the default limit of 1,000 parameters, actually help? Is the limit close enough to not DOS the application?
Which limit are you talking about? The CPU limit, or?
No, the maximum parameter limit in PHP, which will be introduced in 5.4 or so.
Yeah, that works very well. So they limited to, I think, 1,000 parameters. The Tomcat people also had a similar patch limited to 10,000, which is still fine, but 1,000 is very, very conservative. So that works, but as said, only against the case where that is actually in your post data. If you generate a hash table from some kind of other data, like JSON or whatever, then you're going to have the same problem because that is then not limited.
So are there any other questions from the public in here? Okay, no, but we have some time left. Maybe you can show us demonstration again, if it's still running. So I would like to thank you very, very much for your talk here and for the vulnerability that you presented. And let's give them again a warm round of applause.